Hi guys. So at the end of last week's lesson, I asked you to have a play with the Reading University simulation, which showed total internal reflection. If you haven't already done that, please do go back and have a look at it because it's going to help your understanding in today's lesson. So this lesson is on total internal reflection. Let's start by having a look at what our lesson objectives are. Okay, so by the end of today's lesson, you should be able to describe what happens when a ray of light attempts to leave or leaves a denser medium at different angles. You should be able to explain the terms partial reflection, total internal reflection, and what we call the critical angle. And finally, you should be able to give examples of where total internal reflection happens in the real world and where it can be useful to us. So let's start by having a look at a semicircular glass block like the one shown in this diagram. What I'm going to do is I'm going to shine a ray of light at its center. Now, it is very important that it's shone at the center because if you shine a ray of light at the center of a circle, when it enters the glass block here, that angle is always going to be a right angle. It doesn't matter what angle you come from, the angle on entering that glass block will always be a right angle, and that's really important. Why is it important? Because remember, if the ray of light is traveling along the normal, that whole wave is going to reach that boundary at the same time, and therefore the direction before entering and after entering is going to be the same. We are not going to get refraction taking place. You know, if you think about yourself walking along that line with your arms outstretched either side of you, both of your hands are going to slow down at the same time, and so we're not going to get any kind of turning effect. If we were to shine the ray of light to anywhere other than the center, that wouldn't happen. We'd actually end up with one of our hands entering before the other, so part of the wave entering before the other, and therefore you're going to get refraction taking place. And we don't want that. We only want refraction to take place leaving the glass, not on entering. So definitely going to be shining it at the center. Okay, so what happens when that ray of light tries to leave that glass block? It refracts. Now, we obviously need a normal on there, which I've now added. And if you think back to our last lesson, when a ray of light goes from a more dense to a less dense medium, it bends away from the normal. So our angle of incidence here is going to be smaller than our angle of refraction here. We're bending away from the normal. Now, it's worth pointing out here that we're also going to get a partial reflection. So not all of the light is going to leave the glass block. Some is going to be reflected off that boundary between the two media, and that's what I've labelled here as a partial reflection. Now, you've all seen partial reflections. Think about it when you look through a normal pane of glass. Most of the light leaving you and hitting that glass is going to go straight through it, and somebody on the other side of that glass is going to be able to see you. But what you're also going to be able to see when you look out of that window, a faint reflection of yourself. So there is going to be some light bouncing off that glass and coming back to you. And so that's what we call a partial reflection. Most of the light is refracting, coming along that path that I've labelled as the emerging ray, but some's going to get reflected back into the material, and that's the one that's labelled partial reflection. So what happens when we now increase the angle of incidence? Well, I'm hoping because you've done that simulation that I asked you to look at, you already know this. As we increase the angle of incidence, the angle of refraction also increases. Now, we're going to get to a point where if we increase it anymore, the following happens. So here, we've increased our angle of incidence so much that the angle of refraction is now 90 degrees. So this emerging ray, this ray here, is now traveling along the boundary between the two media, so between the air and the glass. So the angle of refraction is 90 degrees. Now the angle of incidence, this angle here, that results in the angle of refraction being 90 degrees, is what we call the critical angle. And that's a really important term that I want you to be able to define. So the critical angle is the angle of incidence that results in the emerging ray traveling along the boundary between the two media. Or to put it another way, the critical angle is the angle of incidence that results in the angle of refraction being 90 degrees. So what happens if the angle of incidence is bigger than the critical angle? Well, this happens. We get what we call total internal reflection. So now none of the light is leaving at that boundary. All of it is being reflected. So we've gone from having a partial reflection, so some of the light being reflected and some being refracted, to all of the light being reflected. Now it's worth pointing out here that this is now effectively acting like a plane mirror, and the angle of incidence is actually equal to the angle of reflection. I also just want to kind of split this up into sections. So why do we call total internal reflection total? Why is it total? Well, it's total because now no longer is it only some of the light that's being reflected, it's all of the light. So in the previous diagrams, we had some being refracted, some being reflected. Now all of it is being reflected, and therefore it's total. Why do we call it internal? We call it internal because it always happens inside a material. Total internal reflection does not occur when we are entering a denser medium. It never happens when we're going into glass or into water. It only ever happens when we are leaving it. And so it always happens inside a material, hence why we call it internal. And obviously, why do we call it reflection? Well, because it's reflection. Okay, so what I now want to do is just summarize this. You don't really need to reproduce these diagrams in your notes a second time. If you want to, as a summary, please feel free to do so. It might be quite helpful, but you've already got all three of these diagrams in your book, so you don't have to reproduce them again. But let's have a look at them. So the first one is when the angle of incidence was less than the critical angle. Now, when that occurred, we had refraction taking place. We also had, I haven't got it in this diagram, a partial reflection. So this is what happens when the angle of incidence is less than the critical angle. So when the angle of incidence is equal to the critical angle, we get this occurring. So now the emerging ray is actually traveling along the boundary between the two media. Our angle of refraction is 90 degrees. And finally, what happens when we exceed the critical angle, i.e. when the angle of incidence is bigger than the critical angle, we get total internal reflection occurring. So I've got here a really nice photo of total internal reflection actually occurring. When you look at this image, it's not instantly clear what you're actually looking at. What you're seeing there is a swimming pool viewed from underneath the water. Now, directly above us in this region up here, we're looking at that surface at quite a small angle, and therefore we haven't exceeded the critical angle. And so actually light is actually coming through the water and striking our eyes. So what we're actually seeing, these kind of things here, these are lights on the ceiling of the swimming pool. But when we start looking at a shallower angle, so we're looking at the water in this region here, now the critical angle has been exceeded, and so we're getting total internal reflection. So we're actually seeing a reflection of the bottom of the pool on the surface of that water. You have all seen this. You must have at some point gone underneath the water, looked up and seen a reflection of the base of the pool on that water. So it's a really nice example that I'm sure most of you will have noticed at some point or another. Where else does total internal reflection occur, and where can it be useful to us? Well, one of the answers is in prisms. So let's have a look at a prism. So here I have a right angle prism. I'm going to have some array of light entering that prism from the left, and I'm going to get it to travel along the normal. So we're not going to get any refraction taking place at this interface because of the fact that it's traveling along the normal. Again, imagine yourself walking along that line with your arms outstretched. Both of your hands are going to enter that denser medium at the same time, and therefore you are not going to get any refraction taking place. When we get to this interface here, so this boundary between the glass and the air, we need to add in a normal. Now, something I haven't mentioned yet, which I probably should have done, is that the critical angle for glass is 42 degrees. I mean, it does vary depending on the type of glass, but in general, it's 42 degrees. Now, here, that angle of incidence, this angle here, is actually 45 degrees. So we have exceeded the critical angle, and therefore, total internal reflection is going to occur. Now, because of the dimensions of the prism, at this interface here, again, we're traveling along the normal, and so the light's just going to pass straight out. Now, I'm going to move on to look at prism undergoing total internal reflection in a slightly different way. But whilst we're doing that, I just want you to think about where we might use this type of prism. What device can you think of that might use that kind of prism to achieve what it wants? So let's look at a different prism. Now in this case, it's still a right angle prism, but I'm going to have the ray of light entering in a slightly different angle. So now I'm going to have it coming in from here. Again, we don't get we don't get refraction taking place on entering because it's traveling along the normal, but we are going to get total internal reflection occurring at this boundary here, and then again at this boundary here, and it's going to come back out again. So two ways in which total internal reflection occurs in prisms. So let's go back to this one. I'm hoping some of you might have realized what this could be used for. This might be used in a periscope. So you would actually use a series of these things to create yourself a periscope, but you get a really nice reflection rather than using mirrors. They tend to use prisms in this way. Okay, and finally, another application of total internal reflection, another way that it is used, is in fiber optic cables. Now that's really important because it's used here for two really important applications, one being communication. You are going to be watching this video on your computer. I'm sure most of that information is going to have passed from a server to your computer along a fiber optic cable. The other application that is regularly talked about is with endoscopes. So that's for kind of doing things like pinhole surgery, any kind of inspection inside the body. Doctors can actually insert a camera and then kind of move it around and actually see inside the body using fiber optic cables. Well, how do they work? Well, let's have a look at the path along which this ray of light is going to travel as it's going down that glass fiber. So I've added this in to start with. Now, if you are ever asked to draw this, and that's quite likely that you will be asked to draw it, it's a very common question in both Key Stage 3 and Key Stage 4 physics. It's really important that you add in normals every time the light strikes the boundary between the glass fiber and the external air or kind of whatever cladding is on the outside of that glass fiber. Because then you can judge the angle of incidence being equal to the angle of reflection like I've got here. Now, look, you don't have to start getting a protractor out and actually start measuring it. We just need to try and do it by eye. I'm now going to add in another normal and again try and make sure that the angle of reflection is equal to the angle of incidence. And in that way, we can bounce that ray of light all the way along the fiber optic until it leaves the other end. So we don't just have normal reflection. This is not a mirror on the inside of this glass fiber. This is actually occurring due to total internal reflection. Now, I've got another really nice image here which shows total internal reflection occurring inside a material. So this is very similar to what's happening inside a fiber optic cable. Okay, so to summarize what we have done in today's lesson, you should now be able to describe what happens when a ray of light leaves or attempts to leave a denser medium at different angles. So what happens when the angle of incidence is less than the critical angle, equal to the critical angle, and greater than the critical angle. You should also be able to define what we mean by a partial reflection, total internal reflection, and the critical angle. And finally, you should be able to give examples of total internal reflection occurring in real life situations. So that's the end of our lesson today, guys. I'm hoping that you've been making notes as you go through. If you haven't, please do go back and make those notes. It's really important that you've got these diagrams so that you can reproduce them if you're asked to in an exam. It's really important that you've got all the text that I've gone through today so that you can go back and revise in time for your end of year exams. Next week, we are going to be going on to look at sound. So we're going to pick up where we left off with sound. So we've finished everything on light. So I will send you through a summary of all the diagrams that you should be able to reproduce and what you should be familiar with. I'll speak to you next week.